In this video segment, we will cover physicochemical properties of drugs and toxicants and discuss the ways that different compounds cross biological membranes. The learning objectives for this video are to compare and contrast ways for drugs to cross membranes, explain the partition coefficient, interpret log p-values, illustrate understanding of the Henderson-Hasselbalch equation, calculate the ratio of ionized to unionized concentration of a drug or chemical, and to be able to determine the relative amounts of a drug to be absorbed across a membrane given the pH of the environment and the pKa of the compound. The discussion of physicochemical properties will focus on lipid and water solubility and ionization state. Then we will discuss how physicochemical properties influence the passage of drugs and toxicants across membranes. Throughout the video, 3 common drugs will be used as examples of the concepts we discuss. These 3 are aspirin, acetaminophen, commonly known as Tylenol, and caffeine. Lipid solubility is defined as the ability of a chemical compound to dissolve in fats, oils, lipids, and nonpolar solvents. A compound with high lipid solubility may also be described as lipophilic, describing its tendency to dissolve in lipids, or as hydrophobic, which describes its tendency to avoid water. Water solubility is the ability of a chemical compound to dissolve in water, which is a polar solvent. Compounds that are highly water soluble can also be described as hydrophilic or lipophobic. A chemical's lipid and water solubility is often described by a partition coefficient, which describes the distribution of a chemical between water and an organic solvent at equilibrium. Often, the partition coefficient between water and octanol, a nonpolar solvent, is used to describe chemical properties. An octanol water partition coefficient can be determined experimentally by adding the compound to a known volume of water and octanol and measuring the concentration of the chemical in the octanol versus the water once equilibrium has been reached. The partition coefficient is then calculated as the concentration of solute in octanol divided by the concentration of solute in water. Often these are reported as log values, demonstrated in this second equation. The lower the log p-value is, the more water-soluble and less lipid-soluble the compound is, and the higher the log p-value is, the more lipid-soluble and less water-soluble a compound is. If a compound is more soluble in water than octanol, the log p will be negative. If a compound is equally soluble in water and octanol, the log p-value will be equal to 0. And if the compound is more soluble in octanol than water, the log p will be greater than 0. If a compound has a log p-value that exceeds 3, it is considered to be highly fat-soluble and will likely accumulate disproportionately in lipid environments such as body fat. This table shows log p-values for a few common compounds, including our 3 example drugs. Notice that our 3 example drugs, caffeine, acetaminophen, and aspirin, all fall in the middle range but vary in their lipid solubility. It is also important to remember that these values fall on a log scale, so the difference between the log p of caffeine and aspirin is 1.2, meaning that the difference in the octanol-water partition coefficients of these 2 compounds is 10 raised to 1.2, which is about 15.8. Therefore, if determined experimentally, about 15 times more aspirin than caffeine would be found in the octanol layer at equilibrium. So now we are going to discuss the 2 main factors that determine the lipid and water solubility of a chemical compound. The first is ionizable groups. This refers to any functional group in a molecule that is capable of being charged. All acids and bases have the ability to exist in a charged or uncharged state. Their ionization state depends on their pKa and the pH of the solution they are in. pH is a measure of the acidity of a solution. It is a logarithmic scale that represents the concentration of protons in a solution. Let's go into a little more detail about ionization. Most drugs are either weak acids or weak bases, and contain at least one site that can reversibly associate or dissociate a proton. The ionization state of a chemical compound depends on whether it's an acid or a base, the functional group's pKa, and the pH of the solution. Let's do a quick review of acid and base principles. An acid is a proton donor. It can give up a proton and become negatively charged. A base is a proton acceptor, so it can accept an additional proton and become positively charged. These reactions are reversible and exist in an equilibrium, with some fraction protonated and some fraction deprotonated. The fraction of protonated and deprotonated acid or base in a solution is dependent on the pH of the solution and the pKa of the functional group. The pKa is the dissociation constant for a particular functional group on a molecule. It is the pH at which the compound is half ionized and half non-ionized. For example, the pKa of benzoic acid is 4. So at a pH of 4, half of the benzoic acid will be in the protonated form, non-ionized, and half will be in the deprotonated form, with a negative charge. If you decrease the pH to 3, the equilibrium will shift and more benzoic acid will exist in the protonated form. In general, if the pH is higher than the pKa, the compound will be mostly deprotonated. For an acid, this will mean it has a negative charge, but for a base, this will mean it has no charge. If the pH is lower than the pKa, there will be a higher fraction of the compound that is protonated. For an acid, this will mean it has no charge, but for a base, this means it has a positive charge. This table shows the pKa's of a range of acids and their conjugate bases. Keep in mind that all acids have a conjugate base, which is the deprotonated form, and all bases have a conjugate acid. The weaker an acid, the stronger the conjugate base will be, and the stronger the acid, the weaker the conjugate base will be. Remember that pKa is the acid dissociation constant. Next, we'll take a look at how this applies to our example compounds. Let's start with aspirin. Aspirin is a weak acid with a carboxylic acid functional group. The pKa of the acidic hydrogen is 3.4, so at a pH of 3.4, aspirin in a solution will exist half in the unionized form and half in the ionized form. The unionized form has no charge and will be less soluble in water, and the ionized form has a negative charge and will be more soluble in water. If the pH is raised above 3.4, the equilibrium will shift to have more molecules in the ionized form, and if the pH drops below 3.4, more aspirin will be in the unionized form. Now let's look at caffeine. Caffeine is a weak base, so it is a proton acceptor. Because the pKa refers to the acid dissociation constant, it applies to the dissociation of the acidic hydrogen of the conjugate acid of caffeine. With a pKa of 14, caffeine will be half ionized and half unionized at a pH of 14. So if the pH of a cup of black coffee is about 5, is most of the caffeine in your coffee in the ionized or the unionized form? Acetaminophen is a weak acid with a pKa of 9.5. Take a minute to think about how pH will affect the ionization state of this drug. So how do you determine the actual proportion of a drug in the ionized or the unionized state at a certain pH? To do this, we use the Henderson-Hasselbalch equation. For an acid, the pKa minus the pH is equal to the log of the ratio of non-ionized to ionized. For bases, the pKa minus the pH is equal to the log of the ratio of the ionized to the non-ionized compound. Using these equations, you can calculate the percent ionization of a drug at a given pH. This figure shows how the percent ionization of a drug changes as the pH gets larger or smaller than the pKa. Because pH is a log scale, small changes in pH can greatly change the percent ionization. For example, when the pH is 1 less than the pKa, 90% of a weak acid will be non-ionized. So why are lipid and water solubility important in pharmacology and toxicology? These chemical properties determine how easily a chemical compound will cross lipid membranes. Biological membranes are lipid bilayers and are more easily crossed by lipid-soluble molecules. So a chemical compound's lipid solubility will influence how a chemical is absorbed into the body and how it distributes throughout the body, 2 areas that we will cover in the next 2 videos. Cell membranes are made up of phospholipid bilayers. Each phospholipid molecule has a hydrophilic head and a hydrophobic tail. Because the phospholipid tails all face inward, they create a lipid environment. Molecules that are more lipophilic are able to pass through the membrane more easily. A molecule's ability to cross a lipid membrane is dependent on size, lipophilicity, and the concentration gradient of the molecule. Gases, hydrophobic molecules, and some small polar molecules will diffuse through lipid membranes if there is a concentration gradient across the membrane. Large polar molecules such as glucose, which is highly water-soluble, and any charged molecules will not be able to cross directly through a lipid membrane. In order for a large polar molecule or a charged molecule to cross a membrane, it must utilize transport proteins. If the molecules are traveling down a concentration gradient, they can utilize membrane channels or carrier proteins to cross the membrane. These are forms of facilitated diffusion. If a molecule is transported against its concentration gradient, it requires active transport through a carrier protein that can use energy, typically in the form of ATP, to transport a molecule against the concentration gradient. Transporter proteins play a large role in determining how drugs and toxicants are absorbed into the body and how they are eliminated from the body, especially if the compound is unable to cross lipid membranes unassisted. To test your understanding of this material, you should be able to answer the following questions. The remainder of the material for this week and next week will focus on the absorption, distribution, metabolism, and elimination of drugs and toxicants. In order to understand these topics, it is essential that you have a thorough understanding of the concepts covered in this video, as they play a large role in all of these processes.